Yes, I'm not going to talk too much about archaeology in Ireland. I'm going to talk about radiocarbon dating, mathematics, exciting stuff for none of you probably, but it's exciting for me. Just a little bit about myself. I've been kind of doing the Bayesian modeling thing, the radiocarbon thing for over 15 years now. I received my PhD back in 2011 in archaeology. I don't have a degree in chemistry or physics. I actually started off doing aeronautical engineering when I first went to university and became kind of bored of science and mathematics after a couple of years, and then switched into the humanities and social sciences, so kind of came back around later in life to this. And I moved up to Scotland in 2011 after I finished my PhD to work for the Radiocarbon Lab, basically providing advice to people and doing kind of the interpretive work on the back end. And just a little bit about my research interests is at the bottom there. So I do actually have an interest in archaeology. I develop research, I lead research projects as well. So I like to take everything back to basics. When I do this, I do various workshops around the world for kind of multi-day workshops on this. This is just a kind of the background bit to kind of how all this works. And the very basics is radiocarbon and how is it produced. It's produced in the upper atmosphere. Cosmic radiation, solar radiation interacts, the neutrons interact with nitrogen atoms, turns it into carbon-14. Carbon-14 oxidizes into radioactive CO2 that's taken up in photosynthesis in plants. Animals eat the plants, and everything's in equilibrium so long as everything's alive. You can see on the right-hand side, there's this little bit about carbon dioxide exchange with the ocean. I'm not going to talk about this here. It's kind of beyond the scope of what we're doing today, but that is a part of the process, and it is something that we do deal with, especially when dating human remains that might be eating things from the sea, but I'm not going to talk about it here. For the most part, though, this mixing in the upper atmosphere is instantaneous for each hemisphere. And so everything's in equilibrium so long as it's alive. Once it dies, this is when the decay process actually takes place. And this is what we're actually measuring, is the amount of decay of radiocarbon within an organism. So this is the actual key element when we start to talk about the Bayesian modeling and sample selection. And I will come back to death. Some people ask, well, how much C14 is there out there? This is probably a bit of an old number because I'm sure we've got more than 7 billion people on the planet these days, but if the whole population was each an isotope of carbon, almost 7 billion would be your normal carbon-12. You'd have about 70 million would be the other stable carbon, which is carbon-13, and less than 1 would be carbon-14. It's very small. There's very little carbon-14 out there, and this is kind of actually drives the different ways of measuring radiocarbon in a sample. These are some of the samples you can measure. We've got human remains, we've got charcoal, pottery, animal bone or antler. There's an AMS up there, so we can use big equipment to do this as well. So two different types of dating. In the past, we had conventional dating. Now primarily everything is done by AMS, which is Accelerator Mass Spectrometry. In both cases, your samples undergo some form of pretreatment. This is to mechanically clean things, you chemically clean things. In the case of bone, you're actually extracting the collagen from the bone, so you're removing the mineral element of the bone to purify it. So there's some collagen being extracted right there on the bone. For a conventional date, then that material is converted into some other form, whether it's CO2 or maybe benzene, depending on the type of dating that takes place. And it goes into a thing called a counter. This is a liquid scintillation counter, and it's counting the actual decays of carbon-14. So as it basically decays back to nitrogen, it lets off a beta particle, and so you're counting those. AMS, on the other hand, we actually take another step in the purification process, and this is the conversion of your sample into CO2 and then graphitization. So you combust the sample, it converts to CO2, you actually purify the CO2 cryogenically, and then that's converted to graphite that's effectively coats some iron filings, and that's what gets put into the AMS for measuring. And here's a wheel. We have a wheel that holds 130 samples at a time, and you go through and you count these on the accelerator. This is our big machine. You can't see it like this anymore because we have a little machine that sits in that little open area there. So this is the one and only photo that I think that we actually have that shows the extent of the large machine. You can climb inside of that tank, for a bit of scale. So the blue box there is just a little bit shorter than me. So it's quite a massive instrument. And this is what it looks like. And the way this works from the left to the right in this is your sample is basically bombarded with an ion source, and off-fly your carbon atoms. As they start to move around, there's a magnet in the left-hand side, and that magnet, because there's a slight difference in mass between carbon 13, 14, and 12, they start to separate, okay? As they separate, you get 3 beams coming through what's the stripper in the middle. That actually breaks up odd molecules that might be within the sample that's not pure carbon. And then it comes around to the next magnet, and they separate even further for measuring. And so you're directly measuring, in this case, these different atoms. You're not counting the decays of carbon-14. You're measuring the number of carbon-14 atoms within your sample relative to the number of either carbon-12 or carbon-13. And in some cases, you'll measure all 3. Generally, you measure either 12 or 13 plus the 14 in a sample. It speeds up the process a little bit. And so that's kind of the big difference. Conventional dates, so when you look back to old dates from sites, and there are these conventional radiometric dates, you're measuring the direct decay. So the older a sample is, the longer you have to measure it, because there's less carbon in it, like carbon-14 in that sample. The more precision you want for conventional, using conventional dates, the more counts you have to have, so therefore the longer it has to sit. So something that's Iron Age, if you want to have a high precision date, you might actually have to let it sit for a week, 2 weeks, a month, to actually get the level of precision that you want for that date. Whereas with an accelerator, you could do the same thing in 2-3 days for 100, basically 100 samples or more. So you have speed. You also have a difference in size. So whereas now for, let's say, something like bone, you could get away with a 0.5 gram to 1 gram of bone to pre-treat to get a nice high precision date. 20 years ago with conventional dating, if you wanted to get a high precision date on, let's say, a human skeleton, you're probably using half or all of a femur to do that. You would need that mass of material to actually do the same thing. And it would take a lot longer to do it. So, but as Katarina had pointed out, with accelerators and these small sample sizes, it also opens up the possibility for a whole bunch of different types of samples that previously weren't available to us. Things like hazelnut shells, but single grains of wheat, let's say, or barley, become available as well for dating. I'll skip that. In the end, you get a result. So this is what most people are used to. You send in a sample, you get a result in the end, and then you need to do something with it. And I like to talk here about age versus date. We just throw around the word radiocarbon date, kind of willy-nilly, everybody says it. They're actually 2 different things. If you're going to be pedantic. So radiocarbon age is actually the uncalibrated result that you get from a lab, and it has a BP attached to it. The radiocarbon date is what you've converted it into something that makes sense on a calendrical scale. I will probably end up saying date quite a bit when I mean age. Forgive me if I do. It's just how we end up speaking about these things. But it is important to know that there's a difference because C14 production isn't constant over time. So we do need to calibrate. This is really important. Everybody generally probably does do it, or you take the calibration that's on the back of your certificate from the radiocarbon lab that you've used. Multiple ways to do this in the past. The earliest was the maximum intercept method. And here on the left-hand side, the pink probability is your radiocarbon age. So that's your conventional result that you get. It's a nice normal distribution. And you go to the 95th percentile or the 2 sigma range. You intersect with the blue, which is the calibration curve. You come down, you get a range. So in this case, it's 351 to 53 BC, or Cal BC. this is no probability associated with this. This is a confidence interval when you're doing this, okay? So you don't really have any information to say, is it more probable that it's early in that range or late in that range? You just don't know when you use this method. And we've moved beyond that now to the probability method, and fingers crossed this actually works. So with the probability method, so you've got your radiocarbon age on the left-hand side, and it has areas of high and low probability. And so you're kind of intersecting all of these with the calibration curve, which itself is a range at 95 percentile as well. And so when you combine those two things together, you end up getting these multimodal probabilities. So you have areas of really high probability for the date, and you have areas of really low probability for the date. And if we go back to that previous date that was shown, this is what it would look like when you actually calibrate it using the probability method. And immediately you can see between 300 and 200 cal BC, there's very low probability that that sample actually dates to that period. The highest area of probability actually falls in the 200 to 100 range. Yeah? And so when we're doing the Bayesian statistics, it's actually these probabilities that we're using for the modeling. So we're looking at the probabilities of the calibrated dates when we're doing that. Does that make sense to everybody? Okay. So now we get to move on to Bayesian modeling. All right, so Bayesian modeling, kind of championed by Thomas Bayes. If you're a Bayesian person, there's an argument over who actually started it really, but we won't worry about that for here. In a nutshell, it is a way to get us beyond eyeballing dates. This is what we generally do as archaeologists when we have a suite of dates from a site. We like to look at it. We use our brains to mentally kind of squeeze things and come up with I think it began at this time, I think it ended at this time. As you saw with the calibration process, you've got statistical scatter that's on your radiocarbon age, yeah. So that creates that normal distribution. Once you've intersected that with your calibration curve, which itself has scatter on it because it's statistically derived as well, you get even more scatter in your final results. So kind of the big point of this is to try to counteract a lot of that statistical scatter that we get in the results. So up behind me, I don't know how easy it is to see, but you have two sets of radiocarbon dates. At the top is site B, the bottom is site A. I will come back to this after I do a little bit with how modeling works. But if everybody take a little moment to think to themselves when they think each site might have began or ended using the eyeballing process, either make a mental note or a physical note onto a piece of paper. That would be great. 3, 2, 1. I'll move on. So Bayes' theorem. So how does this all work? It's actually relatively simple. You've got your standardized likelihood. That's your dates. Radiocarbon dates is what we're talking about here, but you could have archaeomagnetic dates, luminescence dates, calendrical dates, coin dates, any type of date that can be represented as a probability of some sort can be used when you're using things like OxCal. So you have your dates, you have your prior beliefs, and that's the archaeology. This could be stratigraphy. Most people just assume it's stratigraphy. It can be your phasing, though, your grouping of features together on a site. That actually forms part of your prior beliefs as well. And you're combining those formally to come up with a posterior belief, which is it's an answer. And the answer can change. If you have more dates, if you kind of change your read of the archaeology, as it were, then the answer might change as well. In an ideal world, the more robust your model is, the less it's going to change as you kind of alter some of these different parameters, these different prior beliefs that you have about the data. And this is one of the things that we're going to try to kind of get across with sample selection and kind of this question-led way of doing your dating. So in practice, and since the last one worked, this one should work too. You have a start to a site, you have an end, you know your start is before your end. You get a whole bunch of radiocarbon dates, they look something like that. The computer knows that the start has to come before the end, and you're assuming that your sample is a relatively random sample that's of material that's been uniformly deposited through time. That is your most basic model. And that is what Oxcal will do. That's a real model right there with the results. And you can see how those initial probabilities have been squeezed quite a bit in this instance. There's also two purple probabilities that showed up at the end, and those are the start and the end date for this activity. There's no way to directly date that. So you're dating that, you're estimating that based on the dates that you have. And in this case, they show up at 220 and 120 BC. These are simulated dates, so I actually, the 220, 120, that was the limits of the radiocarbon ages that were being used, that were being simulated for this. If we go back to those initial two sites that were being shown, when you run these through the same modeling process, this is the answer that you get. So site B, probably most people did look at that and kind of think 200 to right around the end of the first millennium BC. And I would imagine most people didn't think that the second site was only about 50 years in length. It was quite a bit shorter than the first site. Again, the red lines, these were all developed using something called backwards calibration, where I basically tell the computer, give me a series of dates between 200 and 0, or 1 BC, there's no real 0, between 200 and 1 BC. Give me a series of radiocarbon ages that when calibrated would calibrate between that period. And so that's why you kind of get the picture that you get for the different models. And then the second one was between 150 and 100 was how that was set up. So yeah, so that's kind of how that process works without going into it in too much detail. And hopefully, so the other thing you get is also, you can get duration. Because we can calculate or estimate the start and the end date for a site, we can also say something about how long that site was in use. It's simple mathematics, you subtract one from the other, and it gives you the new probability. So in this case, you can see site A was in use for a very short period of time compared to site B. So site-based models, these are kind of the nuts and bolts of what most people are doing in archaeology, especially within commercial archaeology. And hopefully this can really be, yeah, that's good. Sometimes it doesn't show up so well. So when you see these in publications, these types of figures, and as I go through, these white, the bits that are in the outline, that's your original calibrated date. So that's the calibrated date prior to the modeling. The bits in black, we call these posterior density estimates. They're the modeled date for each of the individual dates. And then you have these parameters. These are these things that otherwise you can't directly date. And there's different types of parameters you can use, but generally, your most basic models, this is what you'll end up seeing as kind of a start and an end and a series of dates. Everything that I showed so far, there was no stratigraphy. So if anybody says, well, I don't have stratigraphy, I can't do Bayesian modeling, well, you can. It's quite simple stuff, but again, it's actually what I do most for a lot of commercial sites because it's the nature of the archaeology. That there's very little stratigraphy. You can have and that's called uninformative prior beliefs by the whole Bayesian jargon. You can have informative prior beliefs. This is stratigraphy. What you see here is a matrix, a dating matrix for a long cairn. And so you've got different phases of activity, whether it's the pre-cairn minted material at the bottom, or people being placed within it at different stages. So you have stratigraphy as well as things that are unrelatable stratigraphically within that. And so you can create quite complex models looking at that. Once you start to get into using informative prior beliefs, you have to be especially cognizant, is probably the good word for it, of your samples, where your samples came from on site, and how they relate to activity on that site. If your prior belief is just, I've got some activity, I want to know when it began and when it ended, you could date almost anything. It's not really going to tell you too much, as far as getting to the nuts and bolts of what's happening. But you can model that, and that's the other way of these other models that I showed. But what you really want to do is to be able to talk about the relationship between the sample and the context and the formation of the context. And with informative prior beliefs, you especially have to be really careful about this. So if you have something like this, a Neolithic enclosure ditch, let's say we have something like disarticulated bone at the base of the ditch, you know, some people will date that. I've come across these types of dates. It's only really a TPQ. It tells you a time after which that ditch was cut, really, because you can't say that that bone itself isn't residual and comes from a time period before the ditch was even cut. So it has very limited utility when you're trying to think about the date of a site, whereas, you know, something like oak charcoal as well would do a similar thing. So, you know, different sample types giving you the same type of information. But if you had articulated bone, maybe you had a discrete dump of charred material that somebody threw into that ditch. You had a pot that broke and was thrown in there and it refit. And you can start to think kind of temporally how articulated bone, well, it hasn't moved around too much because it was articulated in the ground. It went in fresh. So that must have been open when that material went in. A dump of charred material, maybe somebody cleaned out a hearth in the past and that's where they chucked that material. And similarly, the refitting sherds that are in there, these weren't just kicking around on the surface, but they were gathered up potentially and thrown in there if they didn't actually break in situ. So that actually speaks something to the time period when that context was open and forming any date from that material, because you're getting really close in time to the death of the material and its actual deposition. And this connection is really important. And moving up again, so articulated bone, I like to differentiate between articulated and articulating, because articulated, really, you saw it in the ground and it was together. Oftentimes we deal with articulating bone that a specialist has either refit in the lab, or more generally epiphyses. Unfused epiphyses are the best thing for that when they come out of the same deposit, because they only really fit one way. You wouldn't take an unfused epiphysis from one bone and be able to refit it to another bone. Whereas two bones that kind of, they look like they kind of go together, that becomes a bit more tenuous. So again, we can kind of move through this, but this was always a good one, antler picks at the base of a ditch. So they do this in the chalk in southern England because the antlers are being used to actually dig the chalk out, the tines break off. So that's actually a really good bit of material to date. And then, you know, again, disarticulated bone, unidentified charcoal, very limited utility within a model. So we start to build up these pictures of events using the modeling. So the digging of ditches, this is Maiden Castle, the Neolithic activity at Maiden Castle. The top bit is showing you kind of these different events. So the digging of a ditch, when the ditch was filled in by, and then again, as I pointed out before, you can use mathematical, basically subtraction, to then come up with, well, when was that inner ditch in use for, when was the outer ditch in use for, and start to think about kind of the tempo or the dynamics on a site for different types of activity. So if you have a multi-phase site, not multi-period, but literally multi-phase within a period, you could start to do that with the right sample selection. You could say, well, phase one lasted from A to B and it was this long of a time, and then phase two took place. And so you could get into that kind of storytelling for the right kinds of sites. Moving beyond site-based things, you can do seriations as well. Not that this would be more research-based than any commercial-based things, but again, it's informative prior beliefs that are being used to guide your sample selection, and in this case, you know, anything in group T is earlier than S is earlier than R, etc. So that type of informative information can actually give you really refined results, and it's probably not legible up there, but the transitions in this are 20-25 years in the Anglo-Saxon period is what they've been kind of dated to at 95% probability. So with that kind of prior belief, that information, it is possible to actually get really, really refined results. You can go beyond the site. This is one of these simple models for a site. This is some Shelley-ware from London that was dated in London. These are direct dates on residues on pots. So this kind of gives you the date for that material when it's found in London. We also dated it in Perth up in Scotland, and we have a model for that. And we dated some of it from Bergen across the North Sea. Interesting, 3 little site models on their own. You bring the start and the end dates together for these and start to look at those together, and you can see that London Shelley ware, as the name would suggest, it begins in London. That's where it comes into use the earliest. These are large pots that are actually being used to move goods around, so to ship things. Then it shows up in Perth, then it eventually makes its way across the North Sea, and it falls out of fashion at the opposite way. So it really fits with expectation for this type of material. And these are 3 independent models, for 3 different sites, and we're just kind of ripping those probabilities right out of them. And this is a visual comparison. Again, you can compare these mathematically by asking, what's the probability that it begins in one place prior to another place as well. So you can do all these types of things more formally if you wanted to as well. Paleoenvironmental data, so you can actually model paleoenvironmental data, and that's great. As you zoom in, one of the problems with paleoenvironmental things is you're not always able to directly date, say, when something changes in the pollen. Unless you go back, you kind of go through and you date your core, and then somebody does the pollen, and this way these things can run kind of together, and you can go in and you can estimate the date for, let's say, a change in the pollen zone. But you can move beyond that, and you can compare more formally. In this case, disturbance, the Plantago peak, you can see that its date is, say 500, 400-ish BC. It is followed by a peak in cereal pollen, and that little spike there is actually a dendrochronological date for the marsh hill fort that was right next to where the core was taken. So right there you can see that you get disturbance activity leading up to the construction of the hill fort or the marsh fort, and then you get cultivation indicators quite strongly as well. So you can use this type of data to bring together the different data sets as well once we're kind of talking the same language with the probabilities. And again, this is something even more complex, but this is something where it's multiple sites as well as artifact typology. So going through different sites, different cemeteries, and as part of that, there was artifact typology that you can tease out, and you can actually put all that information together. Again, this is something that wouldn't be done on a normal commercial basis, but if you're selecting the right types of samples, down the line, these are the types of things that people can work towards when trying to think about kind of regional chronological questions that they have. So I've very quickly covered kind of the types of models. As I said in the beginning, the site-based stratigraphic models, whether it's horizontal or vertical stratigraphy or next to no stratigraphy, the nuts and bolts, 90% plus of what I do. Everything else below that, I'm actually usually developing a research question, a research project to go for those types of models. Doesn't mean that they shouldn't be thought about. And hopefully as I come through this, people will see, well, actually, yeah, I could see how that might be, something that I date today might fit into a broader research question down the line. So the process itself, it's great to see what you can do. One of the things, how do you actually do it? You define the problem is the first thing. And that is the question. It could be as simple as when did this site begin, when did this site end? But this does come right back to what Katerina was saying about question-led dating. You want to have, you don't just date something to date something. You've got a pit or a post hole with some material in it, let's date it. You want to have a bit of a think about, well, why do you want to date it? How is that date going to inform anything you're going to say about the site? At some point, I probably will be harsh in some of the words that I use, reflecting nothing about anybody in this room because I know none of you, but it reflects kind of my experiences in the past with conversations that I've had with people when trying to select samples. because the first thing you do is you select samples. You can build simulations. Not going to go into that here today, really, but you can, through this whole backwards simulation process, you can actually gauge how many samples you might need or be thinking that you need to answer a question based on kind of your understanding of the archaeology. So if you know that your site, or you feel very confident that your site dates to the period 800, 400 BC, where there's a plateau, if you build a simulation, it's going to tell you to get any sort of precision, you need more samples than you will ever have the money for, unless you have a whole bunch of stratigraphy, really. Whereas other periods, you might not need so much money. Simulation allows people to manage their expectations. If you're to that point, I would say email me or somebody that does what I do, and ask them to kind of help you out rather than doing it yourself, because you'll spend days and days and days doing it yourself. When I train people, I have them do loads of simulations in their period that they're working in, so that they get a feel for how the calibration curve actually kind of interacts with their radiocarbon dates. Because the more models that you've done, the more time that you've spent kind of working within a certain period, you start to intuit. You don't have to really simulate things to start. You start to use it to refine the process as you're going through what is a loop here that's an iterative process of the dating. So, and that's the other key thing. We don't just submit 100 dates and then walk away, but you submit maybe 20 to 50 to start, then you go back, you submit another 10 to 20 after that, where at all possible. I know for some projects, the project timetable, I've got one that they want to submit a few hundred samples in October, and then the last 50 samples, I think they said February was the idea, and that's just the way the project timetable is. So there's a whole lot of discussion between now and October about what it is that is going to make sense, and then fingers crossed they actually get the types of results that they need. But so within this, you identify your prior information. This is a stratigraphic matrix, and so here's two people looking at that matrix and pointing at things. You also want to find your suitable samples, so short-lived charcoals, articulated bone. I'll cover samples in a little bit. And these are the types. I'm going to come back to these types a little bit later. This is kind of a hierarchy. I'll formalize it a bit more a bit later, but you have articulated samples. Those are really good. They're kind of the gold standard when you have articulated animal bone. Don't get it all that often, so you can't really kind of count on having it. Refitting samples, again, don't really have it all that often, and even then it has to be refitting samples of something that you're interested, pottery that you're interested in, generally speaking, or from context you're interested in. Short-lived structural material, stakes, things like that, maybe hazel stakes and things like that. That's pretty good. Again, don't get tons of it. Once we get to the fourth one, that's where we start to get to kind of the nuts and bolts of the type of archaeology most people end up seeing, functionally related material. So hearth material, that's the biggest one that you could imagine. It really is material like that where you see let's say the charcoal, and you go, well, that charcoal is in a hearth, so therefore that's the material that was burned in the hearth, yeah? So that's the functionally related. If you can tell the story about the hearth being cleaned out, then you're looking at it that way as well. So again, a discrete deposit, not a 20-liter environmental sample that happened to have 5 bits of charcoal in it, that you're dating a bit of the charcoal, because that could come from anywhere. You can't really relate that sample to the material directly. The next one is we call circumstantially related material. This would be things like bits of charred remains, let's say, and post holes would be one. You're now having to tell a story about how that material got into the post hole. Some of it could actually be material that was residual from when the post packing went in. But oftentimes what you get, especially if you see the actual post pipe, which you don't always see, especially on truncated sites. The idea there is that as the post is decaying over time, activities taking place in the house, things are being swept up, little bits of material from the hearth and from the activity filter down into the cracks between the post mold and the developing post pipe, and they end up in the bottom of the post hole. But now we're having to tell a story about how does our sample that we're going to date relate to the formation of that context. In all of these, we're having to tell the story about how does our sample relate to the formation of the context. Beyond that, you start to look at things just being TPQs. All you can say is that that context formed sometime after that sample died. So you can't say much more. Every now and then, date things just out of intrinsic interest. And it doesn't really matter. I was telling Katerina last night that one of my projects that I was working on, there was a cattle scapula that was hook damaged, and it was an Iron Age site. And in the report it said, well, there must be Roman activity on the site because beef wasn't being hung in the Iron Age by people. So I was like, well, let's see if that's actually true. And it was late Iron Age for that bit of cattle. So, it's not really helping anything for a chronological model, but it is actually kind of an interesting little question to look at. So, and there's nothing wrong with that, where you do have an interesting question that single radiocarbon date might actually answer for you. So you've gone through, you've thought about all the different samples you have, you've looked at what stratigraphy you might have. You start to, at this point, that big thing has now become something quite a bit smaller, and it's being color coded. What's a TPQ on there, what's not TPQ. So you're starting to select, hopefully, your best samples within that for the dating. When you go to that stage, you start to think, about scientific things. So age offsets. So your wood, short-lived wood versus short-lived species, as well as elements. So if you can identify sapwood on oak, or if you've got little bits of twiggy roundwood, charcoal, that's going to be better than big blocky bits of things. Hazel is going to be better than, say, ash, just because one lives less time than the other, generally speaking. For bone, collagen preservation can be an issue. In acidic environments, you don't even have the bone generally, so you just move right beyond that. Contamination, this says conservation, and if you're doing museum stuff, yes, that would be an issue, but environmental contamination as well. I worked on a site that they didn't know that it had been overlain by an RAF base in the past, and everything was actually contaminated with jet fuel. And so there was loads of material that had been dated, and the dates were all over the place because nobody had actually informed us. And that was, archaeologists knew, but they hadn't actually informed the lab that it needed extra pre-treatment, because there would have been potential for jet fuel all over the site. So yeah, so these are all things that need to be thought about when dealing with these with your samples. The biggest thing, though, is the archaeological consideration. I've covered this already. I haven't formally shown it like this as a nice triangle. Taphonomy. So it's a word that everybody hopefully has heard in archaeology. And in this case, it is that story. It is that the material, it's in the context. How did it get into the context? And how does that relate to the death of the material itself? So that relationship. Because if we go right back to first principles, our date on whatever we're dating, the measurement that we make is based off of when that thing died, whether it was an animal that died or a tree was cut down, a hazelnut was picked off the hazel rod. It's that moment in time that we're actually dating. There's very few things that are different than that. Cremated bone is about the only thing that you would regularly, or more or less regularly, date where it's not the death of the individual. So cremated bone is actually the process of cremation is what you're dating. But pretty much everything else that you would generally date, it's the death of that object that you're looking at. So yeah, so we really kind of hammer home that this triangle is the key thing. Every context that you look at, every bit of material you're thinking about dating, you're always wanting to think about this. I can say hand on heart, when I've actually gone through and worked up sites with people, kind of oftentimes brought in, after excavation has taken place. It's during post-ex usually that somebody brings me up and says, we're going to get 100 radiocarbon dates, and could you give us a hand in selecting the samples? By the time the whole thing is said and done, the number of people that said, had I known this before we started digging the site, I probably would have dug it a little bit differently, because they start to think about these things when they're out there in the field digging the sites, and making notes about what context, what these questions might be, rather than after the fact, because it does at that point start to affect samples that you take, what you decide to flow. I don't know how it works here, but generally it seems people will take 2 to 3 times the number of samples that they actually process after the fact, and it does affect then what they decide in the end that they're going to process as well. So I can't actually speak to this enough today without having everybody just shut down and stop listening. So simulations, again, it's not a big deal. You can do it like this. Everything up here is simulated. Generally, I get a few dates to get started, and then I simulate the addition of further dates. So you go around, you submit those samples, you wait for the results to come back, and you start to revise things. So you get your dates in there. So that's what that simulated model looked like once there were some dates in there. And you might go back through then and decide, well, what other samples might I select to, let's make this a bit more refined. These are bimodal distributions here. So maybe you don't want them to be bimodal. So you might try to figure out, well, what other samples might help me overcome that? Do I have enough money to overcome it? In some areas of the calibration curve, that might be the best that you can do. So this is where then simulation will help you decide, is it worth putting more money at getting a more precise or more refined answer? And you eventually run out of time, you run out of money, and you write it up, is generally how this works. So, and then you publish it, hopefully. So I am going to bore you with taphonomy and sample selection one more time. So, so you get the triangle there, and we'll just come back to this hierarchy of context and sample types. I said before, articulated. I'm just going to kind of talk through some of these briefly. Articulated bones, so like I said, articulated, they're recorded in the ground as such. You might be refitting them post-excavation, or things like unfused elements, like unfused epiphyses. Again, so the idea here is that these samples went into the ground fresh, or pretty close to fresh. They haven't moved around too much, otherwise they wouldn't be, the elements wouldn't survive together. Some people will even go so far with unfused ends of bones to look at the histology of those to see, how abraded are they. If they went in fresh and stayed covered, then you should actually not get too much damage to the ends of them, because that unfused end is actually really, really thin. So that there's little things like that that can be done by specialists to give you kind of more confidence that that material hasn't moved around too much. Carbonized residues, internal. If it's external and it's sooting, if peat fires and things like that, you could actually be dating kind of soot from 5,000-year-old peat instead of the time of cooking. But the idea here is that people were cooking their food and it burned. So long as that food isn't fish, because I said there's this issue with marine things, which you can deal with, but marine stuff is on average 400 years older. But if it's terrestrial things, then you're okay. Cremated bone, charcoal within a cremated burial or redeposited burial, not a problem. Cremated bone does have the potential to, it takes in CO2 from the atmosphere during the cremation process. So if your cremation is taking place with a whole bunch of old peat, let's say, or a whole bunch of old wood, you do actually have the potential to have an offset, kind of an old wood effect, as it were, on the cremated bone, because that's where the CO2 is derived. It's kind of from the atmosphere around the cremated bone. Thermodynamics of a cremation, you get a whole lot of airs just being drawn right in at the base of it and then right up through it. So, you know, it's actually quite violent if you think about it, the air movement through it. So it's generally not a huge problem, but if you are dating cremations, so if you have a set of cremation burials, it is always good to try to, every now and then, if you do have short-lived bits of charcoal within some of those cremations, to actually do pairs for a couple of them, just to double check that your short-lived bits of charcoal are coming up with the same types of dates as your cremated bone. That's indirect association. Short-lived plants, functionally related to their context. This is really important. Back in 1999, a fellow by the name of Patrick Ashmore published a paper in Antiquity about single entity dating, and he was in charge of Historic Scotland's Radiocarbon dating program. And so all of Scotland after 1999 went around just dating single entities. Didn't matter where the stuff came from. And so you've got loads of dates for lack of better things, grain. So wheat and barley from all over sites, and you might get 10, 20 grains of barley from all sorts of different contexts being dated. And these will be literally from 10, 20 liter ditch fills with a couple grains in it, and these somehow date the site. The problem there is that they actually could all date one feature on the site that's been redeposited, because so much of Scottish archaeology is severely truncated, because there's no real relationship between those grains and the deposits from which they were recovered from. And I think this comes back to what Katarina was saying about hazelnut shells as well. We have a huge potential for getting old hazelnut shells coming into younger sites, into younger features. Only a couple years ago, I sat in a meeting with somebody that they really wanted to date some hazelnut shells in a late Iron Age site. My question was, are people really exploiting hazelnuts in the late Iron Age? They had hazelnut shells all over the place. I would be willing to put money, these will be Mesolithic, if not Neolithic, hazelnuts. But he really, really, really wanted to date a couple of them at least. And I said, that's fine, we'll date them. I was acting as an advisor to Historic Scotland at the time, so I kind of had the ability to say no. But I said, no, we'll do two of them. The results came back, and he got them, and the email came through as like, well, they weren't Mesolithic or Neolithic. Well, they were Bronze Age, so they still weren't late Iron Age. So they were residual from still an earlier period when people were using, exploiting hazelnuts a lot more. Oftentimes, I imagine hazelnuts, people probably did eat them in the Iron Age, but you don't get caches of them in Iron Age Scotland. You don't get caches of them in Iron Age England, or large deposits of them, and they're almost certainly, more often than not, they're still attached to the bit of hazel that went onto the fire. It burned, it exploded just like nuts do when they go into a fire, and you've got a nice robust hazelnut shell inside your house kicking around. And so the ones that do actually date from the right time, that's probably what you're looking at. I was actually at a thing last week where they were talking about having dated some they had hazelnut shells, they didn't date them, but you can imagine the people sitting around the fire eating the hazelnut shells and eating the hazelnuts and throwing the shells into the fire pit. I was like, I don't know if they were, because you've only found like 4 or 5 hazelnut shells in the whole site, but anyway. But actually kind of thinking about the relationship between these materials. Charred samples from dumps of charred material. These are always good. So, ovens being cleaned out, hearths being cleaned out. Deliberately disarticulated bones that are deliberately deposited together. Potentially, you're starting to get into some real dodgy territory there, and it's how you interpret those bones. Once you get into carbonized residues on just a single sherd, let's say, it's not really a good thing to date, except for one case, and I'm working on a project that's doing it. And that's because it's grooved ware pottery. And so long as it's coming from grooved ware pottery, and that's what you're trying to date, doesn't matter where the pottery comes from on a site, because you've got a direct date on the grooved ware pottery. So just because it's right near the bottom doesn't mean it's actually a bad sample if it's a good sample to answer the question that you have. And so you have to come back to, again, how does what you're dating relate to the question that you have? And then disarticulated animal bones. Date them if you want to, really. They can be useful, these things, if they underlie something else. So I have dated human burials in ditches where there's disarticulated animal bone beneath in the ditch. And so because that's a TPQ for those burials, it does actually help to constrain the beginning of, you know, when the burials could have taken place. It's only really useful if it's relatively close in time, because if it's pretty far away in time, it makes no difference at all to any model. So yeah, by the time you get to disarticulated animal bone, you're probably wasting your money, almost certainly. So again, I've kind of covered the note on plant remains. So yeah, so when samples aren't functionally related to their context, you're really kind of submitting at your own risk, because they could have come from anywhere. So you have to be really careful about that. When you're submitting your samples, it's best practice to get a full botanical analysis. So you want, what's the species, what bit of the plant. If you're looking at things like charcoal, yeah, so you want to know, is it ash, is it, don't even know what all the species are that you have here, but is it ash, is it willow, is it oak, is it alder? For oak, you know, there's this general consensus, well, oak, old, you know, kind of old wood effect, only if it's, you know, has the potential to be old wood. So if it's twiggy bits, no, it'll only be a few years old. I go so far as to have my charcoal specialist tell me the number of rings in my roundwood charcoal, so I know which ones have 20 rings versus which ones have, you know, say 3 to 5 rings. It might be useful down the line. It doesn't really matter right now, but as your models start to get more and more refined, actually knowing the time width of these individual samples might become useful to somebody. So I ask for it if they're willing to do it. With oak, it is possible oftentimes to see the sapwood versus the heartwood, or at least give a, you know, kind of a compares favorably to sapwood when possible. You know, the issue there is the tyloses, they fill up as it becomes heartwood, so that's the veins basically in the sapwood. And if the material is becoming quite mineralized and it's sapwood, sometimes it's difficult to, they look like they're full anyway, so it can be difficult, but most specialists in the UK, you know, they will tell you if they think it might be sapwood, so you could give that a go for lack of anything better to date. But again, then also thinking about the feature. So I've dated oak from big posts. Actually, this is a good story actually. So these guys wanted to date a post alignment. So we've been going through don't date the oak, don't date the oak. Massive post alignment, and they had hazel in it in one of the post holes. Oh, we'll date the hazel. I was like, well, where'd the hazel come from? Oh, it was there. It's like, well, it's not a house. So I can imagine in, you know, post holes in a house, there's activity taking place in the house. Things are being burned and stuff's getting scattered. This is just an alignment out in the landscape. So is there a hearth nearby? Is there burning activity nearby? Well, no, we didn't find anything. Okay, well, I don't really know how that hazel got in there, but you've got loads of oak in there. So what we can do is, because they couldn't tell what was sapwood and what was not, was use the curvature of the oak and try to find the flattest bits of oak that we possibly could. So at least we knew we were near the outer bits of what was presumably going to be the post that was in there, because there was so much oak that was in it compared to everything else. So again, you're starting to think more about your samples and that context and that feature. And in this case, you know, why would you even expect hazel to be in that feature in the first place, yeah, and not be residual? Yeah, because what you want to keep yourself getting to is that point of Neolithic post alignment. I've got a Bronze Age date. That must be something intrusive. I've got a Mesolithic date. Oh, well, it must be something residual because I know it's Neolithic. Oh, I've got a Neolithic date. Oh, that must be the date of my site. It becomes very circular, and there's no need for that. You know, if that's kind of what's going to happen, there's probably no reason to, again, date it, because all you're doing is confirming what you think you already know with a radiocarbon date. And I know a lot of people, they like that. They want to be able to kind of hang their hat on that peg, but it's not really necessary with the number of dates on features and monument types that are out there. It's probably not necessary, you know, and good use of money. Moving on to faunal and human stuff, element estimated age for people is especially good, even for some animals that might live quite a long time, and the side. The side can be important, one, for people going back, but let's say you have a deposit with mixed cattle elements in it or something like that. You could actually do 5 dates on 5 different cattle from that deposit if you wanted to, assuming that you take the same element from the same side, so that your MNI is right, yeah. Because if you just dated 5 bits of cattle, you could be dating the same cattle 5 times. And again, it allows for people to come back and actually know what you did and what you sampled. And I think that will end up being my last slide, because again, it just comes right back to this. Hopefully everything that I've kept touching on is really about the archaeological consideration. The number of people that phoned me up, Derek, got the wrong date. I was expecting Iron Age, I got Bronze Age. Something went wrong at the lab. I go through the lab records. I see nothing in the lab records to say that we did anything wrong. We can do, and I'll be honest, radiocarbon labs get it wrong. It happens from time to time, happens on my projects. But no, 9 times out of 10, you go back and you start talking about the context and the material that was being selected and submitted. And sure enough, the archaeologist goes, well, actually, now that you mention that, yeah, no, maybe I've got that wrong. So I really can't stress this enough, that this thought process, and that we actually do try to ensure that we are quite thoughtful and quite reflective throughout the whole process of excavation and post-excavation about these considerations right here. So that's that.